So hi guys, today in this tutorial I'll be basically showing you how to do some machine learning on your PCs and basically how to carry out some machine learning techniques on healthcare datasets. So in this video we'll be using a collaboratory system where we can code our machine learning from, and this system is known as Google Collab or Google Collaborative Platform. So the first thing we're going to do is go on the Google Collab. We select the site, and on the site we can basically start a new notebook. Here basically we're going to connect to the system and basically type our code in order to run some machine learning algorithms. The first thing to do when you come on this notebook, you can notice that we have, for example, the title here, and of course we can modify this. We want to write, for example, healthcare dataset, and here we have the connection button. So we have a connection button. In this case we are connected, and over here we're going to basically run our code. So if we click code, we're going to add a new code area where we can import our libraries such as Python, such as pandas, matplotlib, for example, etc., etc. And basically here is where we're going to write our code, and when we want to run our code we're going to click this play button. Play equals running our code. So basically now the next step after accessing our Google Collaboratory area here is we want to basically download some libraries or modules. We want to download some modules related to Python. These modules include NumPy, pandas, matplotlib, okay, and seaborn. They are basically very easy to download. We just write the code and these libraries are going to be downloaded. So what we're going to do next is going to download these libraries. Okay, so import libraries for Python. Okay, and we're going to start importing these libraries. So import NumPy as np, import pandas as pd, plotlib.py, plot as plt, and the last one is import seaborn as sns. And what we're going to do now is going to run it. Okay, so we run it, and this basically is going to run our modules. Okay, these modules basically, why they're important? Because they help us run mathematical models, okay, on a particular data set. So without these modules you can't have graphs, you can't have graphical representations, and you can't even, for example, carry out various actions on the particular data set in question. So these modules are extremely important when undergoing any type of Python coding. Okay, so the next thing we're going to do is download our dataset. We're going to move over to Kaggle, all right, kaggle.com. And basically here we're going to find a dataset related to the Wisconsin breast cancer, Wisconsin, okay, dataset. And basically we're going to have the Wisconsin breast cancer dataset over here. Basically, it's a classic dataset for training and benchmarking machine learning algorithms. So this is a really great dataset which can help us learn and train our machine learning algorithms, okay, via biopsy features. So we have various biopsies taken from the breast, and these are basically classified as either being malignant or benign breast masses. So what we're going to do now next is we're going to download the dataset. So we're going to download it. All right, and we have the CSV file. Now the CSV file, what we're going to do is extract it. So we go to downloads, extract the file, and then we're going to move back to our collaboratory area, and we're going to write some code. All right, so df equals pd dot read CSV, and basically we're going to find the pathway. All right, so we find the path, we go to files, uploaded files, bcra, okay. So the bcra sv, we basically copy path, okay, and the path is inserted into here, and we're going to run it. And we have a very good, it means our dataset or the CSV file has been uploaded. It's a very simple step, guys. It's basically uploading a dataset of your interest. It can be data, related to any, for example, patients or radiographical imaging, etc., etc. And this is basically uploaded into the system, and then you run the code, and it basically uploads the file. Very simple and very basic. Okay. Nothing too complex. The next step is basically trying to identify features of this dataset. So we want to know the shape, how many rows it has, how many columns it has, and for example, how much data there is in the dataset. So we're going to basically carry out this by undergoing the shape function, and the shape function is going to give us basically the amount of, for example, columns and rows present within the dataset. So the next thing we're going to do here in our dataset is identify more information about our dataset, of course. We want to basically get a quick understanding of what the dataset is made of, whether it has columns, rows, the information within the columns and rows, all right? And for example, the amount of benign and malignant cells identified from the biopsy samples. So we're going to start our code here. We're going to write df.head function, and this is going to give us a summarization of the head of the basic information present within the dataset. Okay. So basically we have 5 rows. Okay. The rows we have 5 and 32 columns. All right. So there are 32 columns and 5 rows in our head data. And from this we can see already that there is certain types of data here. All right. So there's a lot of data. Okay, some are benign cells, all right. These are the characteristics of the type of tumor or area, all right. So the area varies a lot. The concavity, the concave worst, symmetry, all right. The symmetry mean, okay. The X area and the X perimeter. Now, from the defined head, we want to know more information about our dataset. So we go down and we want to know the overall shape. So df.shape, and this is going to give us the entire shape of the dataset. So we have 32 columns, 569. In our total dataset, we have 32 columns and 569 rows of information data. This over here is the head, so it's the initial part of the dataset, whilst this is the entire shape. It's a summarization of the shape of the entire dataset if we had to open it up. But because we work usually with very large datasets, which are massive, doing each column or row by itself wouldn't be practical, because I mean 569 rows is a massive amount of rows. You can technically do it, but why do it when you can actually code it out, The next thing we're going to do is check the information of our dataset, what it basically contains. So we do df.info, and this is going to give us the information of the dataset. The dataset has around 569 entries, 0 to 568. Data columns, there are 32 columns as we said before, alright? Now, the type of data is presented over here per column, so these over here are the columns. Each column contains 569 amount of data, and the non-nulls, okay? Now we can also identify how much non-nulls we have, and floats, alright? So to see how many null data there is, we can do another command. We can do df.is null function, and we want to know the sum. Give us the sum. And null data in this case is really good. It's pretty good because we have 0 of 0 null. data here. And it means our data set is fully coded, okay, without any missing data. That makes our data set pretty solid as a data set for interpretation and machine learning convenience, okay? Because if you have missing data, it will of course interact with your results. So having missing data is something that we don't want to have when codifying the data in a dataset. If you worked with SPSS or even Excel before, you also know that if you have missing data in SPSS or Excel, it's going to flow or affect your overall result when you're calculating the, for example, the outcome. So let's say we have a column or data with missing values. All right, this column or data, as we said before, is going to interact with our overall data set. So we basically have to eliminate it. So to eliminate it, we need to insert the code in order for us to delete this column because it's redundant. Drop the nullified column, all right, and we write the axis, all right. So the axis is basically where the column is. Okay, so this, we can run it. And this should drop the column. And if we check the shape again, so if we check the shape, df.shape, we can see that we have 56932. All right, before we had, if we go before, we have 56932. So again, in this data set, we don't have any missing values. Okay, so that's pretty good. And we don't have any issues with another extra column which has no data. All right, so we can continue. So basically, after seeing the entire code of the data set and having an idea of the entire shape and information of the data set, it's time to try and identify the amount of values related to each type of cell, whether the cell is benign or malignant, how many benign cells we have, and how many malignant cells we have in the dataset. This can be done by a type of code, which is basically this code over here, where we define the Y, which is basically the column containing the benign and malignant cells, and the value of counts, how many of these cells are either benign or malignant. In this case, when we run the code, it gives us a benign number of cells, which is 357, and malignant cells, which we have 212. Now, the next step in identifying the data is visualizing the data itself. So we can do this by running a particular type of code where we import the Seaborn library as SNS, and we import matplotlib splt, and then we run the SNS counter. So sns.count plot, and inside we're going to define the data. So x equals define data of the Y, and the label equals the count. And we can run it. Let's see if it provides us with the output. So we can do plt.show. And if we run the function here, we can see that we have a graphical representation of benign versus malignant cells. The orange is the malignant, and the blue is the benign cell count, the amount of cells counted, whether they're being benign or either malignant, and Y is our column. So inside of the column we have benign and malignant cells. Okay. Now the next step is basically running a label encoder. So from sklearn preprocessing import label encoder. And label encoder is basically what is label encoder. So we can get some information if we go to ChatGPT here. What on earth is a label encoder? The label encoder is a class from skitlearn library, which is a popular machine learning library in Python. The purpose of label encoders to encode categorical labels with numerical values. So we're basically changing a categorical label, for example, apple, banana, apple, in this case benign, malignant, into numerical values, which is basically 1 and zeros. In order for us to work with machine learning algorithms, we need to have our data in numerical value. Therefore, in order for us to work with numerical value, we have to convert the categories into numbers. And we can do this by using a particular type of coding, okay? So if we run it, we basically are changing all our data in the Y column into basic numerical values. So we run it, and this should change our code. To continue working on the same type of data and converting the code, we need to eventually transform the code into numbers. So transform categorical data into numerical. And we do this by df.iloc. We give the coordinates, which is basically label encoder y dot fit to transform. So we transform it, and the fit transform will basically contain the location. So we do this, and this should transform our data. It runs, it's okay, so the data runs, and define dot iLocation, which is basically so after labeling our data set into ones and zeros, okay, by using the location and changing the values into 0 and 1 to values, okay, we want to identify the data in a more graphical representation. This can be done by the Seaborn, okay, library, and basically we can import Seaborn and Matplotlib as SN, SNPLT, and run this code. The code basically uses Seaborn and PairPlot, all right? It creates a PairPlot, okay, of the data, and the data locations being basically 0, 1, and 7, and from the column diagnosis. We eventually show all the data in the form of a plot by creating the plots below. So we run the data, and if we run basically the code over here, we can create a variety of output. The output given to us over here basically shows us the various pair plots or the plots between the various data columns for various columns in the data set. For example, here we have the radius mean between the benign and the malignant cells. Here we have the variety of cells, for example, the benign and the malignant cells. And here, for example, we have the texture mean, the difference in texture between both benign and malignant, for example, okay? And we can also see the cluster plots over here between the two cellular types. We have the perimeter means, the area mean, okay? The various area between the benign and the malignant. Now, the benign and the malignant were the blue and the benign were the orange. So we can see, for example, that malignant cells have a greater area compared to, for example, the benign cells. And so is the perimeter, okay? Here we have a legend, diagnosis being 0 and 1. 1 is malignant, 0 is malignant, and 1 is benign. And over here we have the smoothness, okay? So the smoothness mean it apparently shows us that malignant cells tend to be a bit more smoother than the benign cells. I mean, the data is easier to understand by the given graphs over here. And of course, if you have a paper or a research data set, you can use this graph to, of course, extrapolate results from. So after getting the pair plot over here with the seaborne, we're now going to create a heat map, okay? So what is a heat map? A heat map is basically a graphical representation which tries to identify the correlation between the data. If we run a correlation of the data, we can obtain a correlation, however, without a graphical representation, it won't be clear. So if we run a correlation by, for example, doing df.iloc, which is the location, and we correlate, we're going to get data which shows correlation of our data set, okay? So here we have the correlation, we have the diagnosis, with diagnosis, which is 1, it is highly correlated. The radius mean, the texture mean, the area, the smoothness, the concavity, these are all highly correlated. And the level of correlation means the level of accuracy. Let's see if we can do a chart here. Okay, so if we do a graphical representation of the correlation by selecting charts, our correlation obtained, all right, can be seen here. Another way of obtaining a better output in order to visualize the correlation between the various numbers or percentages in our dataset, we can carry out this using a heat map. A heat map, basically what it is a type of graphical representation which gives us the color, all right, related to the amount of correlation we have in our data set. So the darker the color, the more highly correlated, and the lighter the color, the less likely correlated the data is. This gives us a good idea of what in our data set is actually correlated to something else. For example, what is affecting the diagnosis and what is affecting the output, whether it is a benign or a malignant cell. In order to do this, we do the following code. So we basically are going to plot a figure, which is basically going to be our heat map. The figure size, or fig size, we're going to select is going to be 10 by 10. However, you can also make it 5 by 5 or smaller if you want to. However, 10 by 10 is a standard figure. And then you can run the seaborne, okay, heat map. And we're going to place again the location, iloc, and the correlation, which basically shows us the correlation between the data. The CMap is going to be consisting of various colors, okay? And these are going to be defined by yellow to light yellow, okay? So these are light colors, okay? So YL means yellow to light yellow. Then we're going to add some green, okay? And also some blue. So these colors have to be standardized. Otherwise, your heat map won't make much sense. And notation is going to be true. And finally, our FMT, which is basically our how we're going to display the numbers, okay, which is going to be in a percentage with a 0 decimal place in between. So 0 decimal places, and you want it to be a percentage. So the numbers we're going to display are not going to be numerical values, but percentages, okay? So we want a percentage here, and we should run the test. Let's see. So here, I forgot to add an equals, and now it should work. All right. Yes, it actually did work. So this is basically going to be the heat map, and as you can see, we have dark colors, as we saw here before as well, that the more correlated it is an item, the darker the color is going to be. So diagnosis is highly correlated, the area mean seems to be highly correlated, the smoothness, okay, the symmetry mean, okay, and the symmetry mean. So symmetry, smoothness, and area, all right, will all affect the diagnosis. If we want to reduce the size, okay, we can say 5 by 10, for example. Let's see. A 5 by 10 map. All right, this is going to give us a smaller, slender size heat map. We can also have a 5 by 5. let's see, 5 by 5. And 5 by 5 is going to give us a smaller map, okay? So basically it is just the size. And this is the color. So yellow, green, blue. If we want to change it to green and blue, it should give us a different color scheme, all right? So what you type over here is extremely important to the output, okay? So when you're creating a heat map, always think about the figure size, okay? What size you want it, the location of your data, the CMap, what colors you want to represent the data with, all right? Between, for example, going from light yellow, yellow, and then blue, green, blue, all right? And the type of output. So the output over here you can see is a percentage. So they are a percentage at 0 decimal places. Of course, this can be changed, all right? You can, for example, remove the percentage, and this is going to give us a 0 decimal place output, okay? But we want it as a percent because percentages are better representations. So basically, the next step in training our models or our data is going to be basically feature selection. So what on earth is feature selection? Feature selection, by its name and definition, is basically the selection of features which can be variables, or data, or values, which we want to select from all the data set. Therefore, we reduce the dimensionality of the data. The data from a massive dimensionality is reduced, and the overall quantity of data is streamlined. Therefore, we get more selective towards particular features we want to select from the data set. So we can write the title, which is feature selection, and feature selection is going to basically split our data into independent and dependent datasets. So the independent is going to be the X, and the dependent features are going to be the Y. So basically what we can do is X equals to df.iloc. So we have the columns to 31 dot values, and we have y equals df.iloc, which is the location, and we have our columns, which is basically 0, 1 dot values. So basically these are going to be our features, okay? So basically when we click our button here, it goes green, and this basically takes the data, all right, accepts the data that we input over here. Therefore the X is defined by location, all right? The columns we give 2 to 31, the values, and the Y, which is the dependent variable, is going to be basically the location from 0 to 1, values given. The next step is to split our data, okay, into a ratio. So we're going to give a ratio of 80:20 ratio. Basically from sklearn dot model selection, we're going to import train test split. From this we're going to get xtrain, the xtest, ytrain, and ytest equals train test split. which will contain basically the x and the y, basically the dependent and independent variables. It will contain also our test size, which is going to be 0.20, and the random state, which is going to be 0. If we run this test, it should go green. Yes, it's green, and therefore our data set is now selected. So we have a data set which was split into 80 to 20% ratio. Okay. Next on, we're going to go to create a standard scaler. So a standard scaler, basically, so now we're going to import from sklearn the standard scaler. What is a standard scaler? The standard scaler basically is a machine learning technique which limits the amount of variance or deviation in our data set. So basically, if we go to, for example, ChatGPT, it tells us that the standard scaler from scikit-learn, all right, the standard scaler is a pre-processing technique used in machine learning to scale features so that they have zero mean and unit variance, which means they help to improve the performance of a certain algorithm. We can see that from sklearn.preprocessing we will import standard scaler. So we can actually just copy this instead of typing it. It's faster actually. And we just throw it in there, okay? Next, what we want to do is the X-train and the test. So in machine learning, when we're carrying out machine learning, we either have a trained data set or an untrained data set. Therefore, supervised or unsupervised learning techniques. In this case, we're going to have a training set. So we're going to use xtrain, all right, equals the sc.fit transform. And we have the xtrain. Also, we have, for example, the xtest equals dot fit and we have the xx test. So this basically, the standard scaler is going to limit our variance, basically, all right, before we go on to more in-depth machine learning techniques. So this did not take it, all right. What was the problem here? Yes, C is not defined, okay. So standard scaler. Okay, I found. Okay. So SC is not defined, so we need to define SC. So SC basically is a shortcut, which means standard scaler. And it's going to be a function, all right? So scalar, all right? So let's see if it takes it. Is not defined, okay. So why is it not defined? So basically, let's try now by changing this to scalar. Okay, so basically what I had here is a spelling mistake. So this wasn't read because actually instead of standard scalar, it had to be standard scalar with an E, okay? So such a simple thing can create a total havoc. So let's go ahead and shoot it, okay? And press the button over here, and yes, the data was taken, it's accepted. Okay, that's good. Next up, we'll go and create a logistic regression model, which is basically a more of the classical machine learning techniques when investigating a particular data set. So basically, after doing feature selection and basically modifying our data set, we have seen here that we identified the main types of cells, the benign and the malignant, And next up, we want to see whether there's a relationship between the dependent and the independent variables. In order to do this, a common technique of checking the association between the dependent and independent variables is basically logistic regression. So logistic regression, basically, we can check the outputs of the algorithm by using different algorithms for problem solving. Okay, these include, for example, random forests and decision trees. In order to carry out logistic regression, basically we have to, of course, code it out. And the first thing we're going to do here is basically write the title, what we're going to do. So logistic regression, and the next step will be basically importing some library. We're going to import a library from pandas known as random state. So random state, we import the library, and next we're going to define the models. We're going to define the models, which basically are xtrain and ytrain. Xtrain and ytrain. And from which we're going to have sklearn imported. Okay, so we're going to import from sklearn dot linear model import logistic regression. The log is equal to logistic regression, which is basically a function, and inside of it we have random state, which is equal to 0. And we have log fit, and again we have xtrain, and we have ytrain. Okay, so we run the test here. Let's see if it takes it. No. So we have a problem in the in the data in the type of code. Okay. Let's see what's the problem. So let's see what's the problem here. So we basically have to add an E because I forgot to add an E here. So this should solve the problem. Okay, let's see if it solves the problem. And yes, so it's green, and basically the input was accepted. Okay, so choosing the regression algorithm, select an appropriate regression algorithm based on the problem and the data character. Common choices include linear regression, ridge regression, all right, decision trees, random forests. So basically, after passing the decision tree classifier, we're now going to run another algorithm, which is basically a random forest classifier. So why use a random forest classifier? The random forest classifier basically is used for both classification and regression. It is based on decision trees. It produces a more accurate final prediction. It is basically a collection of decision trees. It reduces the overfitting. It is highly accurate, and it is also scalable. So in order to run the random forest classifier, we basically are going to do something similar with the code. So from sklearn, we're going to import the random forest classifier, and from that we're going to basically the forest is going to be equal to, in this case, the random forest classifier is going to take number of estimates equals to 10, we have a criterion and we're going to have random state, which is equal to 0. Then we're going to run the fit, so forest.fit of the model, which again is going to contain x-train and y-train. Okay, if we run this model, it should be accepted. Let's see if it takes it. Yes. And actually the model runs, it works. That's pretty good. Okay, so here we have both forms of classifiers. We have a decision tree classifier and also a random forest. Basically, the random forest is working or based upon the decision tree, okay? And it provides a more accurate prediction and basically more scalable with a higher accuracy than the decision tree. So basically, after running the classifiers and the logistic regression, all right, and this having been accepted, we're now going to see the accuracy of the models. So here we're going to write the title, accuracy of the models, including the logistic regression, all right, which is basically logistic regression, decision tree, and random forest, okay? And in order to do that, we're going to run some Python code. So we're going to write the print function. The print function is going to give us the accuracy of the logistic regression here, okay? And it's going to basically give us the log score of the x-train and the y-train. And we're also going to copy this for the other two forms, for the other two classifiers. We're going to copy this basically for the other two classifiers. So we're going to have a print here, all right, and another print. So one is going to be decision tree, and one is going to be random forest. So here we're going to have the tree score. Here we're going to have the forest. And of course, if you know Python code, we have to return the data. So return log logistic regression. So we have to return the log score, the tree, and the forest. So there was an error here. Let's see what the problem was. Okay, so here we have an error. So we're going to change this, okay? That has to be within the parentheses, okay? So this should be within parentheses. Now let's see if it takes it. Okay, it did not take it apparently. So when coding, you're always going to find some errors, all right? There's always going to be some problem here. Let's see what the problem is. Log is not defined. Okay, so basically what it was the spacing. So when you're coding with Python, it's very important to actually take care of the spacing, okay? So here, because we have a we have a function, okay? So define models is a function. And inside of the function, we have the logistic regression, the classifier, and the random forest. Because these are within the model's definition, okay, we have to space out the typing of the code, okay? So the code must be spaced. There must be an indentation. This is not red because it's a title. And also the print, okay? The print should also be spaced out. And after this, it actually runs, okay? So the return will give us the log, the tree, and the forest. Now, in order to check the accuracy, we can run the model, all right? The models of X and Y. Basically now, after running our logistic regression and also our decision tree classifier and random forest classifiers, and printing the scores, okay, we basically here return the scores which are the log, the tree, and the forest. After this, we want to see how accurate our model is, okay, whether it's 100% accurate or less than that, okay. In order to do so, we're going to run some code here, which is Python code, okay. Instead of typing out all the code from scratch, basically, I'm just going to paste the code because it's most of it is repetition, all right. So basically, the code here, we're going to import again logistic regression, decision tree, random forest, and also from sklearn metrics, we're going to import our accuracy scoring system. Okay. Here, as we see, we have a logistic regression model, all right, using the X train and the Y train, the log of the logistic regression, and the log fit, which will return log. Decision tree and random forest are also here. And assuming X train and Y train are your training data sets, okay? Logistic regression equals logistic model, decision tree equals decision tree model, and of course the random forest equals the random forest model. All right? After all of this, we're going to print basically the accuracy of the logistic regression, the decision tree, and the random forest. If we run the code, all right, it should give us the output. So the output here is logistic regression is 0.95, all right, accurate. We have a decision tree which is around 1 in accuracy, and random forest which is 1 in accuracy. Of course, as we see here, the type of model used, whether it is a decision tree or a random forest, the random forest and the decision tree are actually more accurate than the logistic regression models. So the next step after checking the accuracy of each model, all right, we have seen that each model has different accuracy amounts. So the logistic regression has a particular accuracy, whilst decision trees and the random forests seem to have a better level of accuracy. After this, we can actually run a confusion matrix. And what on earth is a confusion matrix? A confusion matrix basically helps us to predict how much false positive and false negative values we have in our data set. If we have too much false positive and false negative values, okay, the data set won't be that accurate. So if we go to medium over here, we can see actually what on earth is a confusion matrix. So a confusion matrix for machine learning basically consists of predicted values and actual values. All right. The actual value and the predicted value, which are too positive, give us a true positive value. The predicted value is positive and it is also positive. All right. So the output and the predicted output are both positive. All right. And that is good. A false positive is basically type 1 error. The predicted value is positive, but in reality it is false. And a false negative is a type 2 error, where the predicted value is negative, but actually it is positive. And why is this important? A confusion matrix is a n times n matrix used of evaluating the performance of a classification model, where the n is the number of target classes and the matrix compares the actual target values to those that are predicted by machine learning model. So the predicted and the actual are either negative or positive. A true negative is a Tn and a false positive is a type 1 error, and a false negative is a type 2 error. A good model is one in which a high Tp and a high Tn rate is present, whilst a low false positive and a low false negative are also present. So one good model or one good data set is one which has true positives and actual true negatives. Okay, so the data, whether they are benign or malignant, the cells are benign or malignant, are actually true and actually false. Okay, so the models are actually predicting a real diagnosis, not having an imbalanced data set. all right, which gives you a true, which gives you a false positive or a false negative, because these patients will be misdiagnosed and therefore their management will be different. Okay, now how do we run a confusion matrix? Okay, so to run a confusion matrix, we have to basically carry out some code. Okay, so confusion matrix, and we're going to do the same thing from sklearn dot metrics import from sklearn metrics. We're going to import the confusion matrix. So we're going to first carry out logistic regression confusion matrix, which is going to be this. Okay, I just copied the code because it's actually faster. Okay, so the logistic confusion matrix, CM is confusion matrix. Okay, equals confusion matrix. You have Y test, logistic model predicts the X test. So the true positive, the true negative, the false positive and the false negative, and the logistic accuracy. The logistic accuracy is basically a sum. So the logistic true positive and true negative over the logistic true positive and true negative. All right? It is technically a sum. And eventually we're going to print out the models over here. The next, we're going to go for the decision tree and the random forests. So decision tree confusion matrix. So decision tree confusion matrix here is the same, all right? It's basically the same as the confusion matrix over here. We can also say this for the random forests. Now, if we run the code, it should give us a confusion matrix with the amount of true positives and true negatives. In fact, here we can see that we have a confusion matrix over here. So the type 1 and the type 2 errors in each of the models is extremely limited. For logistic regression, we have 4, all right, type 1 error and 2 type 2 error, whilst most of them are actual true positive and true negatives, okay, with the regression accuracy being 94%, approximately 95%. The decision tree confusion matrix has around 7 type 1 error and 3 type 2 error, with around 91% accuracy, and the random forest has around 3 and 1 type 1 and type 2 error with around 96% accuracy. Okay, so these models give us how accurate our actual data set is, whether it has a lot of false data or true data. After running our confusion matrix over here, as we have done before, the confusion matrix, we're going to check whether our output here is correct or not. How do we know that the true positive or the true negatives are actually true or not? Okay, we can't really know. Sometimes in our data we might have information which is a false representation of reality. Therefore, in order to see whether the data is real or not, we have to run a accuracy model. We run the accuracy of the model, how accurate our model is. The accuracy of the model is going to check whether the data output is actually predicting what it is meant to predict. So model accuracy is going to give us an important output. It is going to show us basically whether our data is really false or really true. Okay, so from sklearn metrics, we're going to import classification report. We're going to import the classification report, and from sklearn learn metrics, we're going to import the accuracy score, which is going to give us the score of the outputs, whether they're accurate or not. Okay. Now, so for I in the range, which is basically length model, again, this is a function. Okay, so when we have a function, we always indent. Okay, so there's a space here. Don't forget the space. Okay, print the model, and what we will print is going to be which is going to be I. I is the range of outputs. Okay, print classification report, and the classification report is going to contain the y-test, the model is going to be basically I, dot the predict. Next, we're going to write the accuracy, score, which will contain the y-test, the model we want, which contains I, and again the predict, which is going to contain x, which contains predict. However, these are wrong. These should be brackets. So these should be brackets, otherwise our test won't run, and these also should be brackets. Okay, so these are the x. Okay, this is the I contained in the model, and this is the y-test. After this, we're going to do the print. So we're going to write print function with Python, and this is going to give us an output. Hopefully, let's see. The code, okay, was not working here, so we're going to correct the code for models. Basically, what was happening is that the code wasn't being read, the models were not being read, and basically what are our models? Our models are basically the logistic regression, the decision tree, confusion matrix, and the random forest. So what we're going to do is we're going to add them. Okay, so in the corrected code here, we're going to add our models. The models are basically going to be the logistic model, the decision tree, and the random forest. For I model in enumerate the models, okay, we're going to print the model, the classification report, and the accuracy score. All right, and this should work if we click it. Yes, it actually works. So over here, what we're seeing, guys, is basically we have three models. We have model 0, which is basically our logistic regression report. We have model 1, which is the decision tree, and model 2, which is the random forest. And here we have the precision, okay, the recall, the F1 score, and the support. So the precision here is 97, okay. The model 1 is around 95, and model 2 is 98. Of course, as we said before, the random forests are going to have a higher precision, all right, compared to, for example, logistic regression and decision trees. And that makes sense. So overall, the accuracy is higher for our random forests, and it's actually lower for our decision tree. So our final step in evaluating the dataset is basically going to see which of our models is the most accurate and whether there's a difference between the actual and the predicted. In this case, we're going to select our random forest classifier because it had the best accuracy score over here, and we're going to basically try and predict the output. So prediction equals the model we want, which is going to be model 2, and we're going to predict the x-test. We're going to print our model prediction, our model's prediction. Our model prediction, we're going to print again our model, print prediction, and we're going to print function, and we're going to print the y-test. Okay, this should give us an output, and this is wrong as well, so that should be like that. This is capital, it's uppercase, it's wrong, it should be lowercase. Okay, so after correcting the code, we can see that our model's prediction is here, and the actual prediction was over here. So our model is going to predict that the first score is going to be a 1, okay? And the other one is going to be a 0, 0, 0, okay? For example, here we have a 0, and actually it is a 1. The actual is a 1, okay? So the model prediction is 0, and this is a 1. This is a 1, and this is a 0. Here we have, for example, a 1 and a 0, a 1 and a 1, okay? So we're seeing whether the actual and predicted, there is a difference between the actual and the predicted, okay? What this type of prediction is doing is that it is checking that our model prediction is actually the same as the actual prediction. In some instances, this is not going to be the case, and this is because of the level of accuracy of the model selected. So what this helps us do is basically select our model and check the overall prediction versus the model's prediction. So this is basically the end of the video. I hope the video was interesting, guys. It was a basic tutorial on some machine learning applications in healthcare, in analyzing a healthcare dataset, in this case, breast cancer prediction, as you can run various models on various types of datasets you might have in your projects. Okay, so thank you for watching the video, guys, and see you in the next video.